welcome back. Willkommen back zum Nick Does Maths. I'm Nick, this is Maths. Welcome minions, we're going to do some fun maths today. What have we got? We've got some circular motion. We've got a particle of mass m sliding from the tippy top of this smooth hemisphere. Any given point, it's got a velocity v. Basically, we want to show that whilst it's on the sphere, r is equal to this, and then we're going to find its velocity as it leaves the sphere. Fair enough, seems like a plan. Right, first things first, we've put in its mass, its weight with that angle theta right there. That's kind of cool. Remember, this is a hemisphere, so that length there is a. Let's crack on. So let's do some forces. Let's look at the forces acting towards the center of our circular motion. Well, what force is acting that way? We've got mg cos theta minus the reaction force, and that's got to equal to mv squared times the radius, mv squared over a. Silly boy. Right, now, vertical circles, almost always, we're going to want energy, conservation of energy. Now, at the start, I'm just starting up here on the top of my sphere. How much energy do I have? Well, I've just got gravitational potential energy, mgA. Now, by the time I've slid down to this point here, where I'm making this angle theta, right, that if we look in sort of radials, we're making this angle theta with the vertical. What do we have? Well, we've got mg. Now, what's the height? That is a cos theta. And we've got some kinetic energy at that point. Now, what do we want? We want r, but no v. So let's get rid of v. Let's call this equation 1. Let's call this equation 2. So if I go equation 2 divided by a and times 2, what do I get? I get 2mg minus 2mg cos theta is equal to mv squared over a. And mv squared over a is precisely equation 1. Which is mg cos theta minus r. And here, that should do the trick for me. So let's bring that over here. R is equal to 3 mg cos theta minus 2mg, which is what we want. mg times 3 cos theta minus 2. The smiley face of destiny. Right. Okay. Well, let's find v in terms of a and g as it leaves the surface. Now, how do I know when it leaves the surface? Classic bit of mechanics. This reaction force changes depending on theta. Now, if we have a look at this, right, 3 cos theta minus 2, 3 cos theta minus 2, that's going to look like this. And as theta increases, at some point, my reaction force hits 0 and then becomes negative. But the reaction force cannot be negative. So really what we're saying is, when does it leave? When does it leave? Well, it leaves when cos theta is equal to 2/3. That is when it leaves. Now after that, we can go check either that or that one. It doesn't really matter. Let's go for equation 2 at that point. So if we have a look at equation 2, first of all, the m's can cancel out. And we know that cos theta is 2/3. So it's telling me that GA is equal to 2/3 of GA is equal to v squared over 2. Well, that's telling me that 1/3 GA is v squared over 2, which tells me that v is square root of 2/3 GA. Et voila! Simple. Simple-ish. The only thing holding us back is the fact here that we are looking at R. Whenever you have an expression for the reaction force, remember, it has to be positive. So as soon as you see something that could become 0 or negative, we start thinking, maybe that's going to be an interesting part of the question or something I need to consider. Either way, I have fulfilled my end of this particular deal, which is I am called Nick. I did some maths. You watched it, dear math magicians, on YouTube. I hope you found it interesting. If you did, drop us a comment, drop us a like, drop us a subscribe, and hit that bell so you know when the next one of me babbling wildly about mechanics comes up. Otherwise, see you soon.